Hi, Alex. My name is Mr. Remaker. I'm a math teacher here at Cathedral. I teach the AP statistics class as well as pre-calc, but I will be doing my best to try to get you through first semester of regular statistics. I'll be using some of Mr. Wankowitz's materials just so in the event you do return to campus, you'll seamlessly get back into his course. We're going to be starting off with Chapter 3 in your curriculum. And we're going to be looking at the relationship between variables. And we're going to start by looking at the relationship between variables that are categorical in nature. So going back to some stuff you know from algebra, you know about x and y variables from algebra. In statistics, we don't really use x and y notation. We're going to call these things our explanatory variable and our response variable. So when you look for relationships in data, there's going to be one of the variables called the explanatory variable, which you might think of like an input value, or it's going to be something that might allow us, might help us to make a prediction on some particular output. And that output is called the response variable. So the response variable is the output. It might be the reaction. It might be the dependent variable. And it's going to be sort of the outcome. So will knowing one thing help us predict another, for example? To make it more specific, we'll look at a couple of examples here on this next slide. So in part A here, the opinion about tax reform and political party membership. So if you were investigating opinion about tax reform and political party membership, what's meant there is that you would be looking to see if knowing someone's political party, meaning do they identify as a Democrat, Republican, Independent, Libertarian, Socialist, etc., is that going to help us make a prediction on their opinion on tax reform? So for example, perhaps after you do some investigation, maybe you might determine, oh, Republicans are more in favor of this piece of tax reform, and Democrats are less likely to support it. So political party would be the explanatory variable, and their opinion on the tax reform would be the response. Part B of this example, anger level, low, moderate, or high, and whether or not a person has coronary heart disease. So in this case, we are going to try to determine, is someone's level of anger, low, moderate, or high, going to help explain or predict whether or not that person may be more or less likely to end up with heart disease. For example, maybe someone who is angry all the time, has a high level of anger, might have a higher occurrence of coronary heart disease. And so the anger level is the input, and the coronary heart disease would be the output. But the specific terms here are explanatory and response variables. So the next question is, instead of just running a bunch of numbers and showing a bunch of computations, how do we display the relationship between two categorical variables, thinking maybe this is in a paper that you're writing, it could be in a newspaper article, etc. We want a visual way to represent relationships in categorical data. And there's a couple of ways in which we can do it. The first of those is going to be what's called a side-by-side bar graph, which you see on the left. And the other is going to be what's called a segmented bar chart, which is shown on the right. The data that's being graphed here is based on a survey that was done in the United Kingdom. They asked kids aged 9 to 17 in the United Kingdom what superpower they would most like to have. And they gave them a list of options, which included the ability to freeze time, the ability to fly, the ability of telepathy, super strength, or invisibility. They kept track of what the girls said, and they kept track of what the boys said. And in order to visually display what they found, if you look at the graph on the left, they made what's called a side-by-side bar graph here. So if you look at invisibility, these two bars are of basically the same height. So that means there's about an equal percentage of female and male respondents who voted invisibility. No real relationship there. But if you look next at super strength, the purple bar above super strength is noticeably higher than the blue bar above super strength. If you look at the key above, the purple bar is the male respondents and the blue bar is the female respondents. So from that bar, you can see that males are more likely than females to vote super strength. And you can continue to look at the difference in bar heights for each of the other superpower options. And you can see that boys are more likely to vote for some of those, girls are more likely to vote for some of those things. Another option, this segmented bar graph on the right, takes two bars, both go up to a height of 100%. Meaning if you look at all of the females that responded, the 100% of all of the females that responded, you can then chop up this bar into different pieces based on what percentage of the females gave each of the 5 possible answers compared to what the boys said in terms of their responses. You can then compare and contrast the relative heights of each of the different colored segments. And again, you can notice that boys are more likely to answer some superpowers. Girls are more likely to vote for other superpowers. And this may allow you to notice some relationships between gender and superpower preference. Now, if we're starting from scratch and it's our job to make one of these types of graphs, the segmented bar graph, for example, there are specific things you want to include on your graph in terms of how this is going to happen. First of all, you have to make a decision on which variable you're going to choose to be the explanatory variable and which variable is the response variable. What's your input? What's your output? The second thing is then you're going to label your horizontal and vertical axis, which using some algebra notation, the explanatory variable goes on your horizontal axis, or what you think of as the x-axis. The response variable goes on our vertical axis, or what in algebra we'd call our y-axis. After you label your axes, then you are going to actually draw your 100% bars, and then you have to actually segment them. You're going to go ahead and, chop them up based on what percentage of females and males gave each response. This is going to involve some calculations. The calculations are going to be on specific percentages. After you go ahead and do that, well, I guess I kind of did this in a slightly different order. You will have to go ahead and do your calculations, I would imagine, first. Calculate your percentages. Draw your, you're actually going to not draw, but you're actually going to then segment up or chop up your bars based on the math that you did up above, and make sure that you include a key so that you know which colors or which parts of the bars go with your different subcategories. It'll only really make sense if we look at a specific example. So hopefully you're a little bit familiar with the Titanic disaster. The Titanic happened to crash on its maiden voyage across the Atlantic, hit an iceberg, sank. Some passengers did successfully survive. They got onto lifeboats and were able to survive and get rescued, but many passengers died. There were not enough lifeboats to handle all of the people on the Titanic. So if you take a deeper dive into the data and look at this two-way table that's provided here, this gives you the raw numbers based on, did the passenger purchase a ticket in first class, second class, or third class? And did that particular person survive the Titanic, or did they die? We have each of the numbers in there, including the total number of people that bought each kind of ticket, the total number of people that survived, the total number of people that died, and the total number of people that were ticketed passengers on the Titanic. Now, in order to find the relationship, we have to calculate percentages, but we have to calculate the correct percentages. So in terms of our explanatory variable here, it's going to be class of ticket. The response variable is going to be their survival. Did they survive or die? So what we want to do is compare what happened in each of the three columns. So specifically, we're going to compare everybody who was in first class to everybody who was in second class. And lastly, we're going to look at everybody who was in third class. So what the notation Mr. Wenkowitz used right here, the S-1, that is going to be the proportion of people who survived if they were a first-class passenger. So the denominator of our computation is going to be 319, because that's the total number of people that meet the condition of having a first-class ticket. And of the 319 people in first class, 197 of them happen to survive. If we calculate into a percentage, round it off to the nearest whole percent, because I feel like rounding to the nearest whole percent, 62% of the people survived. We can go across. The D over here means died, given they were in first class. So 122 of the 319 people in first class died. That's going to be 38%. Hopefully it makes sense that the two percentages there must add to 100, because everybody in first class either survived or died. In second class, there were 261 people that had second class tickets. 94 of those individuals happened to survive. So that's a survival rate of 36%. The death rate was 167 deaths out of those 261 people, or it's got to be 64%, because the two percentages have to add to 100, because everyone in second class either survived or died. Lastly, third class passengers, we had 151 survive out of the 627 people in third class. That's a survival rate of 24%, contrasted with the death rate in third class, which is 476 over 627, which has to be 76%, again, because everybody in third class either survived or died. So those two numbers must also add to 100%. So looking at the numbers, you can see a relationship. The survival rate was highest in first class. The survival rate was noticeably lower in second class, and the lowest survival rate was in third class. Now, visually, if we want to display this relationship in a picture, so the numbers show us one story, but the picture will show us another story, okay? Or at least make it more visual. So we have this skeleton graph here, two-dimensional graph. The horizontal axis is going to be representative of the explanatory variable, which is going to be the class of ticket people had. And they were either in first class, second class, or third class ticket. There's no numerical scale on the horizontal axis because class of ticket's categorical, not quantitative. The vertical scale is going to be measured in percentages. Mr. Wenkowitz already put the percent label on that vertical scale. So then we have to draw our bars that will go up to 100% for each of these subcategories of first, second, or third class passenger. The widths of the bars should be consistent, but the widths of the bars don't really mean anything. And the distance between the bars doesn't really mean anything. Now we're going to segment this bar based upon survive and death. So if we scroll back up, we look at in first class, 62% of the individuals in first class survived. So if I go up to a height of about 62 on the vertical axis and draw a cross there, now we've chopped up the first class passengers into two categories. If I sort of shade in this part, so if you're doing this with a pencil, just like lightly shade that in or make some, markings like that. We can then contrast it in second class. It was a 36% survival rate. So I'm going to go to where 36% is on the vertical scale, segment this bar up into the two categories of survive and die. And then the last survival rate was 24%. So I'm going to go up to about 24% on that vertical scale and segment the third class passengers together. The last part is going to be the key. And so I let the shaded part represent survived, and I let the unshaded region of the two bars represent, or of the bars represent the passengers died. So what a reader could now do looking at this chart is look at the relative heights of the shaded regions. And they could easily see that the survival rate amongst those in first class is higher up than the survival rate in the second class, which is higher up than the survival rate of the third class. So now visually you can see the size of the difference, and that there was a pretty substantial difference in the survival rate between first and second class. There was a difference in survival rate between second and third class, although not quite as substantial. And there's a gigantic difference in the survival rates between first and third class passengers based on the relative size of the shaded regions of each segment. Now, by looking at what's going on in this graph, we now should be able to determine that there is an association between the two variables. Their association exists because we do know the value of one of the variables is helping us predict the value of the other. Meaning, if you told me that your great-great-great-grandfather was on the Titanic, and you told me that he was a first-class passenger, that would give me information that he had a higher chance of survival in there. So knowing the first outcome, or knowing the input that they were a first-class passenger, helps me predict the outcome, knowing that, oh, that person had a higher chance of survival. Doesn't mean they were guaranteed to survive, just means they have a higher likelihood. If we go back up to the first segmented bar graph we looked at about the superpower preferences, if we talk about what's going on here, you could now make a statement about, you could compare, sorry about that highlighter there. You're going to compare males to females. So now you could make some statement like, males are more likely to want, well, what are males more likely to want? Freeze time, because you can see this yellow segment is much longer than that yellow segment. Males were more likely to prefer orange, which is super strength. You could then go on to say females were more likely to prefer flying, and females were more likely to want telepathy. Lastly, you could say where they're the same or similar, and that is for invisibility. There was about an equal amount of male and females that voted invisibility. So you could obviously go into more detail. I didn't want to write a whole paragraph here, but you could explain now in like a paragraph format and describe the relationships that you notice in the data. Now, there are situations where variables may not have any relationship. You might think there is. So what would it look like if a segmented bar graph showed no association? Well, if we made up some data, this is not what actually happened above. This is just pretend. But let's say what happened if we did this survey again. Now, in this one, notice the relative sizes of the yellow, green, blue, orange, and I guess teal colors there are all basically the same. So this would be an example of a situation where there is absolutely no relationship between gender and superpower preference. Meaning if you told me that the person surveyed was a boy, it would give me no extra information about what their superpower preference would be. It wouldn't matter if the person was a girl or a boy because the votes were basically identical across the genders. What do we see? An association, perhaps. Well, this is the one we made. This is a slightly more professional-looking segmented bar graph of who died and who survived on the Titanic. That's just a computer-generated version of what we made earlier. Just probably looks a little prettier than what I drew. And then the last thing to be aware of on our last slide here is a big warning, which is going to be consistent throughout statistics. Just because two variables are associated does not mean that one causes the other to happen. Okay? Determining causation is an important thing in statistics, but this particular data does not allow us to determine cause and effect. It just allows us to determine an association. We'll talk more about cause and effect later on in this course, I'm sure. Anyway, I'm going to be sending you an assignment, which is some practice problems dealing with problems such as these, and then try them. You'll send them back to me or let me know if you have any questions, and we'll go from there. So thanks for listening.